Okay. So hello everyone. Welcome back to the new chapter 4, which is about the expectations and distribution summary. So if you're watching this video, it means that you have survived more than halfway through this course already, because chapter 3 is the longest chapter. Okay, takes about, let's say, more than 10 videos. So if you can survive that part, okay, and the last 3 chapters is gonna be, let's say, not so difficult, because for chapter 4, chapter 5, and chapter 6, we are going to use the concept that we have learned in chapter 3. So there will be no concepts actually. Okay. So let's get started. Why do we have to study this chapter? Okay. So if you are talking about the distribution, remember in the chapter 3, I have given you the distribution, right? That is to find the f, the g of h of some variables. It's gonna be the fully specified function. However, in the real world, what we observe is not the distribution, but it is the data that we have seen. So sometimes specifying the distribution of some variables is a little bit daunting at first. So in order to get the picture of the data or the distribution that we are going to study, okay, we are going to find the summaries. For example, the expectation, the variance, the skewness, the kurtosis, or many other things, okay. So in this chapter, in chapter 4, we are basically talking about the theories of the summary of the distribution. For example, expectation, variances, okay, the medians, or let's say the skewness, okay, and correlation, okay, covariance, some of those other things, okay. And in chapter 5, we are going to look at some of commonly used distribution, okay, and this distribution. So chapter 4 and chapter 5 is going to be in parallel. Chapter 4 is going to be theory, and chapter 5 is going to be a little bit more practical, okay. So in this video, we are talking about only the expectation. So let's get started by the easy stuff first. Okay. I hope that after chapter 3, you are not scared by this kind of long definitions. Okay. So the expression of x is sigma x fx. That's all. Okay, that's all. And what does the below paragraph say? Below paragraph say that in order to find the expectation, this one must be finite. These two must be, let's say, at least one of them must be finite. So there are, let's say, 4 cases. The first case is that this one is finite, this one is finite, fine, no problems. The second case is that this one is infinite, but this one is finite. So it's going to be infinity. That's easy. Okay, the third case, this one is finite, this one is not finite. So it's going to be minus infinity, that's okay. However, the last case, the final case is that this one is infinity and this one is minus infinity. So infinity minus infinity, it is undefined in this case. Okay. So if both sum are infinity, x does not exist. So at least one of them must be finite. But for most of the time, we do not care about this condition because most of the time, x is bounded. If x is bounded, so this one surely it must be bounded. Okay. For the continuous variable, we change from sum, okay? We change from sum to integration. And these technical conditions are the same. So this one, at least one of them must be finite. If this one, both of them are infinite, ex does not exist. Okay. Now let's go to the first example. Suppose that a random variable x has a continuous distribution for the clear variable. Okay. So this one, actually this one is a Cauchy distribution actually. Okay. So first that this is the PDF. Okay, it's the PDF. How to find the PDF? You have to integrate, right? But how to integrate this function? Remember this kind of basic formula from the calculus. So we have not used this function that much, okay? But when it comes to this function, this formula is extremely important. And the second one is that we have to find that, okay? So for this one, we have to, I think it's wrong. I think it must be x. It must be x. Okay, and I think it must be x because it is indicate x as x. So x times this function is infinity. X on the infinite even has infinity. So e of x of x is. Okay. So let's go to the graphical representation here. So this one is a PDF. It is extremely similar to the normal, right? The Cauchy one is extremely similar to the normal, but it is a little bit heavy tail. They have a heavy tail. So for this one, it is extremely hard to believe that e of x could not be found, right? But if you look at this one, you at the right hand side, it's gonna be, let's say, it is the x of x. Okay, so look at the right hand side is 1. So it is, the slope is going down, yes, but it's going down extremely slow such that, okay, such that the area is infinite. And this one is similar, it is infinite, so the area is extremely large for x of x. Okay, so this one is the intuition behind it. So the next one, expectation of the function. So first, if you find the expectation of the function, is that you have to find. So if x has a PDF, that is f. So if you want to find the expectation of y, that is e of y, right? E of y is belongs to the g of y. So you have to find from f of x to the g of y first, using the concept of functions of random variable. Function of random variable. And then from g of y, we can integrate y, dy, dy. And this one is going to be the expectation of y. Okay. Okay. So next one. The second example. X belongs to fx. It's going to be the function like this. But Rx is equal to 1 over x, and then we can find the PDF of y is equal to Rx. So how can we find it? How can we find it? It's gonna be what? It's gonna be f, right? F of what? It's gonna be x, but we have to write it in terms of y. I inverse of y. And then times what? And then times y given x, right? It's gonna be this formula. Because we are applying the chain rule. Okay, we are applying the chain. We are derivative with respect to x, so we will find this one, and this one. So dy is something like this. And we have e of y. We have y and d. Dy is this one. Okay. So sorry about what I have said in the last video. Because actually we do not have to find the distribution of that function. We could find, okay, actually I lied you in the previous slide because that is extremely intuitive way to think about. But what actually all of us in the statistician world do is that, okay, is that we have the x belong to fx, right? and we have y is equal to rx. We do not have to find the gy at all. The thing that we are going to do is that we're going to integrate, okay, rx fx dx. And it's gonna be e of y. That is all that we do. And this approach is surprisingly correct. Okay, so we do not have to do the gy anymore. Okay, we don't have to do the gy anymore. So what's the proof? Let's say we are going to prove it by the discrete case. Okay, so sigma y g of y is probably that rx equal to y, but we can what? We can flatten it out into the double summation. The double summation of x such that rx is equal to y fx. Okay, and for this one, okay, and for this one, since y is equal to rx, we can push rx inside. Okay, be something like this. And if we equate sum of y and sum of x such that rx equal to y, these two double summation is the same as the single summation of all of x. Okay. So this one, okay. This one is what actually we all do. Okay. So the common name is law of unconscious statistician, because we all do. We all of the statistician do without realizing this theorem. Okay. Without realizing this theorem. Or some textbook we call this one as lotus. Lotus. L is for the law. Okay. O of, okay. I think actually this the law of the unconscious and what? And statistician. That is the lotus law. Okay. So the third example. An appliance has maximum lifetime of 1 year. The time x until it fails is a random variable with a continuous distribution, something like this. Okay. So the thing that you should do is that the time of x is fails. Okay, the time of x is going to be x 12x, something like this. Okay. But suppose we want to find square root of x. Okay. ey is going to be the same, right? So we replace x by square root x. But 2x is the same. 2x is the same, and we get 4/5. One caveat is that e of gx is not equal to g of ex, except one special case that is a linear function. But for general, let's say the square root is 1. Okay, these two may or may not be equal, but in general, it's not equal. Okay, so the fourth example is the example in finance. We are talking about the option, and we are going to use the Lotus law of unconscious statistician. Okay, so you're offered an option to buy a certain number of shares of the stock 1 year from now, and the price, let's say $200. Okay, suppose that the price X of the stock of 1 year from now is 260 and 180. Okay, so we could do the diagram something like this. Okay, so now it's 200. Let's say not now, sorry. So this one is any number. It doesn't matter, but what matters is the future, because we find the option. Okay, so with the probability P, the price is gonna be 260. Okay, and probability of 1 minus P is gonna be 180. What are the payoff? This one is the stock price, is the X. What are the payoff? Payoff, it's gonna be function of X. So remember that the option is not the obligation, okay? Option is not the obligation, it is the right, okay? The right to buy or to sell, but you do not have to exercise this right. For example, if X is 260 and you are allowed to buy at 200, you can get the profit of what? 60. How? Because you exercise this option to buy $200 and sell in the market of 260. So the payoff is going to be 260 minus 200. It's going to be 60. Okay? But the other case is interesting, okay? 180. Let's say if you exercise this option, what happens? So you buy from the market 200, right? And then you sell in this market, you get 180. So payoff is gonna be 180 minus 200 is gonna be minus 20. It is wrong. It is wrong because you can choose to let this option expire. So you didn't do anything. If you do, you get minus 20. It's gonna be the silly option, okay? So instead, you got 0. Okay, that's better than minus 20. Okay. So this is the payoff. And we do not have to find the P and 1 minus P again because we can use the lotus, okay? We can use the lotus to associate 60 with P and 0 with 1 minus P. Okay? Let's proceed to the next slide. By ignoring the dividend and transaction cost, it's going to be something like this. Like what I have described before. Assume that an investor could earn 4% risk-free rate during that year. The fair cost of option would be E of Y, 0, 1 minus P, 60, 60 times P, okay, 1 year from now. And the fair price now, okay, that is we are going to convert from the future value to the present value because 60p is what we get 1 year from now. 1 year from now, say t equal to 1. But if you have to convert into present value, the present value is when the t is equal to 0. And we get this number, okay? Assume that the present value of mean of x is equal to current value of stock price. In other words, the expected value of buying 1 share and waiting 1 year to sell is the same as investing current cost of stock risk-free for 1 year. So this one is a little bit reasonable assumption, right? Because by taking either option, because the level of riskiness is similar, so you could get, let's say, the similar payoff too, okay? If assuming that they are risk neutral because you're using the concept of the expected, okay, the expected number. So the E of X is gonna be 200 times, okay, times 1.04. Times 1.04. That is the opportunity cost of fund, and 200 is what you get. Okay. And this one is going to be the expected value from the option. Okay. So the P is equal to 0.15, 0.35, leading to the C is equal to $20.919. That is the risk neutral price of option. Risk neutral because what? Because let's say option one is what? Is buy the stock 1 year from now. Okay. And the option 2 is buy the option. It's risk neutral because if they do not care about the risk at all, okay, but actually option is riskier, okay, in the real world. But if they are risk neutral, that means these two they care about the expectations. If they care about the expectations, they are going to yield the same payoff. That means from this one, we are going to get the risk neutral price of option. Okay. So we have found a lot of expectation in this video, but it is tedious. If you have to find this all the time, okay, it's very annoying. And in the next lesson, we are talking about some properties that will ease some of the calculations. Okay, so see you next time.